Congratulations on completing the first task and on working out how to generate two-dimensional random vectors using what you learned about random variables during the first 3 weeks of the semester. In this exercise, I'm going to teach you how you can use what you now know about generating random variables to solve integrals. In particular, I'm going to teach you a numerical method for solving integrals that is known as Monte Carlo integration. This numerical technique is used extensively in a range of different areas of applied mathematics because calculating integrals is important in many fields of applied mathematics, and because when we must integrate over many different variables to obtain the integral we desire, Monte Carlo is really the only numerical algorithm that we have. We're not going to solve a high-dimensional integral in this exercise. Instead, you're going to calculate the area for a quarter of a circle of radius 1. Obviously, we know that this integral is equal to pi by 4, as the problem can be solved analytically. This exercise is not about solving integrals analytically, however. It is about solving them numerically. So let's start by revising what we have learned about solving integrals numerically in other modules at other levels. Let's suppose that we want to integrate this complicated looking function. When we calculate an integral, remember, we want to calculate the area under the curve. Consequently, one way we could attack this problem numerically is as follows. We could draw a regular grid of squares underneath our curve as shown here. We could then differentiate between the squares that are underneath the curve and those that are not underneath the curve as shown by the green line here. We then count the number of squares that are underneath the green line and multiply this count by the area of a single square. As the figure here shows, we do not get the exact value of the integral when we calculate it in this way, but we can get reasonably close. Furthermore, we can control the accuracy of our estimate by simply adjusting the sizes of the squares that we divide our grid into. Lastly, this method is relatively easy to implement on a computer, and the algorithm can be easily generalized to work in 3 or higher dimensions, although in practice, we cannot really do this, as it will rapidly become too expensive to run. With all this in mind, in the first couple of tasks in this exercise, we're going to try and write a computer program that uses the algorithm that I've just explained to calculate the area of a quarter circle. The first step in doing so is to work out how to write a program to generate the grid of regularly spaced points in 2 dimensions that is shown here and that we require. Let's suppose that the squares of which our grid is composed have a height of a and a width of b as shown here. Our numerical algorithm will test if a particular square is underneath the curve of interest by testing whether the midpoint of the square is underneath the curve. Our program is thus going to need to generate the midpoint of each of the squares shown in the grid. For obvious reasons, the y-coordinate for the midpoints of all the squares in this bottom row is 0.5a. The x-coordinates are then at 0.5b, 1.5b, 2.5b, 3.5b, 4.5b, 5.5b, and 6.5b. It should now be clear to you that we can generate the coordinates of all these points by using the Python code that is now shown in the bottom right-hand corner of the slide. Y-vals here obviously contains the y-coordinates of all our points, which are all the same. X-vals, meanwhile, contains the x-coordinates of the point, which go from 0.5b up to 6.5b in steps of p. It should also be relatively clear to you that we only need to modify the code slightly if we want to generate the midpoints of this row of grid squares. In particular, we only need to change the part that sets the list y-vals, so that instead of setting the elements of this list to 0.5a, we set the elements of the list to 1.5a. We could, therefore, generate the midpoints of all our cells by simply copying and pasting this code, the code shown on the slide, 5 further times, and by adjusting the values that we set the elements of the list y-vals equal to. As I have explained multiple times, however, good programmers avoid using copy and paste and instead try to use for loops. We can thus write this whole batch of code using the double loop shown here. As explained earlier, the inner loop here then runs over the various possible x values in each in the particular row of our grid. The outer loop then ensures that we run over all possible rows of our grid, and hence that we generate all the points that we need. Hopefully this concept of double loop is thus relatively clear, and you will thus have no problem with the next task. Good luck.